So good morning students, welcome back. Today we'll start new lesson number 6, electromagnetic induction. In short, it is said to be EMI. So before explaining the meaning of electromagnetic induction, we'll start with magnetic flux. That we also did in previous chapter in magnetic property of substance, okay, in magnetism. So let's start with, first of all, magnetic flux. It is represented by phi b. Look at students, what is magnetic flux? Okay, we are having two definitions. First of all, we'll discuss the theoretical definition. Okay, suppose that is a particular surface, partial surface ds, okay, particular area, okay, and these are the magnetic field lines. These are the magnetic field lines, okay, that passing perpendicular to the surface. So those, what is the first definition of magnetic flux? Those magnetic field line that passes perpendicular, normal to the surface, is said to be magnetic flux. Okay, and what will be its mathematical definition? It is defined as the scalar or dot product of magnetic field and that particular surface area, phi equals to b dot ds. So this is said to be mathematical form of flux, and that is theoretical. Those magnetic field lines that passes normal perpendicular to the surface are said to be magnetic flux. Either the scalar or dot product of magnetic field and surface area is said to be magnetic flux. Okay, when we remove dot, there comes cos theta by the property of scalar or dot product. Okay students, now we'll discuss its unit. Look at students, we'll find the unit of magnetic flux. Okay, so we'll find in both the system MKS as well as in CGS. Okay, for finding, first of all, the unit of magnetic flux, okay, in MKS system is Weber. Weber is the name of scientist. So unit of magnetic flux in MKS system is Weber, while in CGS system it is Maxwell. So magnetic flux is a scalar quantity, okay, and in MKS system its unit is Weber. In CGS its unit is Maxwell. That is the unit of magnetic flux. Okay, now students, we can also get the unit of magnetic field. Here I am going to tell you, for finding the unit of B, okay, divide, the formula will project it as phi by ds. The unit of flux is, magnetic flux is Weber and area meter square, and Weber per meter square consists of 1 Tesla. It means Tesla, Nikola Tesla is the name of scientist. Tesla is a unit of magnetic field in which system? In MKS, and 1 Tesla consists of Weber per meter square. Okay, B equals to phi by ds. The unit of magnetic flux is Weber in MKS system, okay, and area will measure in meter square, and Weber per meter square consists of 1 Tesla. So Tesla is a unit of magnetic field in which system? MKS. We can also get in CGS. In that condition, look at, Weber is replaced by Maxwell and meter square replaced by centimeter square. In that condition, it become 1 Gauss. It become 1 Gauss. So the Maxwell per centimeter square equals to 1 Gauss. Gauss is also the unit of magnetic field, but in which system? CGS. And Tesla in MKS. And there is a relation, 1 Tesla consists of 10 to the power 4 Gauss. That is the relation between Tesla and Gauss. 1 Tesla consists of 10 to the power 4 Gauss. Okay students. Now students, to discuss one of the most important topic, that is the meaning of this chapter, electromagnetic induction. So before starting that, we'll discuss Faraday's experiment for EMI, for electromagnetic induction. What he did, he made a circuit, Faraday made a circuit, he took a coil and connected with a galvanometer. Okay, he took a bar magnet, north and south pole, that is a bar magnet. Okay, every magnet release magnetic flux. This is what? This is magnetic flux. When we bring a bar magnet, look at students, when we bring a bar magnet close to the coil, passing flux through the coil will increase. It means passing flux through the coil will change. And what he observed, okay, it produce, look at, it produce current and EMF in that circuit. Whenever we bring a bar magnet close to the coil, in that condition, passing flux through the coil will change. As a result of change in flux, it produces current and EMF, current and electromotive force. That is the potential difference between terminals, okay, through the battery. So when we bring a bar magnet close to the coil, passing flux through the coil will change. The flux will increase. As a result, it produces current and EMF, and galvanometer will shows deflection due to the production of current in circuit. Such phenomenon is said to be electromagnetic induction. What he did, when we took away, okay, aside the bar magnet from the circuit, passing flux through the coil will decrease. Here the flux increases, but here the flux decreases. But the common thing is what? Either the flux increase or decrease. The flux changes. So what is the essential condition for the production of current and EMF? Flux should be changed. When we took the bar magnet away, aside of, okay, from this circuit, the passing flux through the coil will decrease. As a result, it produces again current and EMF in opposite direction, in another direction. Okay. And third condition, what we did? When there is no relative motion between bar magnet and coil, the coil is placed in the state of rest. Okay, flux passes, but that is what? That is constant flux. In that condition, galvanometer is showing zero deflection. So what he observed, what we observed, that whenever we bring bar magnet close to the coil, either away, in both the condition flux changes, and whenever the flux changes, it produces two component, current and voltage, current and EMF, electromotive force. Such phenomenon is said to be electromagnetic induction, and this is Faraday's experiment. Understood, students? So now I will explain you with the help of a circuit diagram. Now that will easier to understand. Now students, let's start. So look students, this is a galvanometer. Okay, this is the galvanometer, and this coil, and this is the coil. Okay, I connected a galvanometer with the help of a coil. Okay, and look students, the galvanometer does not show any deflection. Look at, when we bring a magnet close to the coil, look at, it's showing deflection. Look at students, it's showing deflection. Why? Because when we bring this magnet close to the coil, this is coil and this magnet close to the coil, then what happens? Passing flux through the coil will change. It produces current, and galvanometer always detects the amount of current. Look at. So this is the practical demonstration of electromagnetic induction. Look at students. When we bring a magnet close to the coil, it's showing deflection. Away, it's showing deflection. But when it remains constant, it does not show any deflection. So whenever the magnetic flux linked with this coil changes due to the relative motion of magnet, okay, it produces current and EMF. This coil produces current and EMF. Such phenomena is said to be electromagnetic induction. So you are seeing the practical demonstration of electromagnetic induction. Okay, students. Now, students, on behalf of Faraday's experiment, okay, we did today. We'll discuss now Faraday's law of electromagnetic induction. Faraday gave two laws. First, we'll discuss the first law. What he did on behalf of experiment, again, he took the coil and connected with the help of a galvanometer. Okay, and this is the bar magnet. Okay, north and south. When we bring bar magnet close to the coil, towards the coil, passing flux through the coil will change. As a result, it produces current and EMF, current and electromotive force. Such phenomenon is said to be electromagnetic induction, and this is Faraday's first law. So the definition of EMI is Faraday's first law. Look at, I'm going to repeat. Whenever we bring a bar magnet close to the coil, in that condition, passing flux linked with the coil, passing flux okay, linked with this coil changes. As a result, it produces current and EMF. Okay, such phenomenon is said to be electromagnetic induction, and this is Faraday's first law. Now students will discuss Faraday's second law. What is Faraday's second law? Look at students, the Faraday's second law. It states that the rate of change in magnetic flux, the rate of change in magnetic flux always equals to induced EMF. It means if the rate of change in flux is more, it produces more EMF. When rate of change in flux is less, it produces less EMF and less current. So basically, what is Faraday's second law? E equals to d phi by dt. The rate of change in flux, the rate of change in magnetic flux always equals to induced EMF. Okay, and when we use minus sign, that is said to be Lenz law. That is said to be Lenz law. What is the minus sign showing that? According to Lenz, minus sign will show that induced EMF always opposes the rate of change in flux. What is Lenz law? Lenz law states that, okay, in an electrical circuit, okay, the direction of induced current and EMF are in such a way that these two factors always opposes the rate of change in flux, the factor which are responsible for its production. It means EMF always produced by the change in flux, okay, and EMF will oppose that factor, rate of change in flux, that the factor which are responsible for its production. Due to change in flux, EMF produce, okay, and EMF will oppose this. Rate of change in flux produce EMF, and EMF always opposes the rate of change in flux. It means Lenz law states that the direction of current and EMF, the polarity of current and EMF are in such a way in circuit that these two factors always opposes the rate of change in flux, the factor which are responsible for its production. Okay students, so these are the Faraday's and Lenz law. Understood students?